Hey everyone! In this video I'm going to show you what bitwise operators in C++ look like and how they work. Knowing what the binary system is and how numbers are stored in binary will help you here. So we already know a lot of C++ operators. Today we'll learn about a few more, specifically bitwise ones. Bitwise operators are operators that don't work on numbers as whole values but on the individual bits inside those numbers. Normally we deal with numbers as integers like 10 or 25, but the computer stores them as sequences of bits, zeros and ones. Sometimes you need to control those bits directly. For example, with bitwise operators you can store several logical values inside a single number, for instance in 1 byte. They're also often used to turn individual flags on or off, like graphic settings, key states, access modes, and so on. Bitwise operations make that simple and efficient. You can also see bit manipulation in systems, programming, and game development, for working with ports, graphics, network packets, bit masks, microcontroller registers, and so on. Or, for example, you'll run into bitwise operations in some algorithms too, like hashing, XOR encryption, and checksums. Bitwise operations provide a simple and fast solution, and that's exactly what we're going to break down today. And we'll start with bitwise AND. That's the regular ampersand symbol. We've already used it when we wanted to get the address of some data or when we created references. But it can also act as a bitwise operator, so it kind of multitasks. It's a binary operator. That means it needs operands on both sides, like literals, constants, or variables. For convenience and simplicity in the examples, I'll use variables of type unsigned char because they only take up 1 byte. And for nicer, clearer code, I created a type alias for it and called it byte. So we have two variables. I gave the first one the value 51 and the second one 170, but written in binary. Then I create a third variable and assign it this expression. Here we're using the actual bitwise AND operator. It works like this. It takes each bit of its operands and compares them according to these rules. Based on that, a resulting bit is formed for the new value, and it goes through all the bits like that. Both of our variables have 8 bits. For convenience, we'll compare them from top to bottom, starting on the right and moving left. We see bits 1 and 0. If we look at the rule, 1 and 0 gives 0, so we write 0 at the bottom. Next we see 1 and 1. By the rules, that's 1, so we write 1. Then we see 2 zeros, and the resulting bit is 0. Then 0 and 1 gives 0. Then 1 and 0 gives 0. We go through all the remaining bits like that and end up with this number. It's 34. You can notice that bitwise AND works the same way as logical AND, just with bits instead of conditions. If both bits are 1, the final bit is 1. In all other cases, it's 0. That's why it's called bitwise AND. You might be wondering, why would I even need this operator? Let me explain. Imagine a situation where somewhere in your code you need to store some variables. The first one says whether a fan is running or not, basically, is it turned on or off. The second variable says whether it should be rotating or not. And the third variable stores the fan's speed level, 1 for low speed, 2 for high speed. All 3 variables together take up 6 bytes. Now imagine you're writing a program for a microcontroller where memory is very limited, and you realize that you only have 1 byte available. How can you fit all those values into 1 byte? Easy, you just store them in bits. Let's answer a few questions. How many bits do we actually need for the first variable? Just 1, because it only has 2 states. What about the second? Also 1, for the same reason. And the third one, 2 bits, because we've got 3 possible values: 0, no speed, 1, low speed, and 2, high speed. All of those fit nicely into 2 bits. 0 is 00, 1 is 01, and 2 is 10. That means for all the settings, or flags, as they're often called, we only need 4 bits. But we can't create a variable that's only 4 bits. We can make one that's 8 bits, so let's create a variable that stores all these settings. It takes up 1 byte or 8 bits. Then we decide what each bit stands for. We only need 4 bits, so we can ignore the leftmost 4. Let's say the first bit controls whether the fan is turned on. If it's 0, the fan is off. If it's 1, it's on. The second bit controls whether the fan rotates. If it's 0, don't rotate. If it's 1, rotate. The third and fourth bits are for the speed level. If it's 0, 1, that's low speed. If it's 1, 0, that's high speed. Knowing that scheme, can you describe these two fans? The first one is turned on, not rotating, and running at low speed. The second one is turned on, rotating, and running at high speed. That's what optimization looks like. We saved a whole 5 bytes and we lost nice readable verbal names, and unfortunately that's not enough. We also have to teach the program how to read those bits and decide what to do. Let's start simple. If the fan is on or off, we'll print a message. How do we do that? We need some way to extract just the first bit of the number. We can use Bitwise AND for that. For clarity, we'll create a constant that shows which bit should be set when the fan is on. In our case, only the rightmost bit should be 1. All the others should be 0 because we don't care about them. And that's how we can check whether some flag is set. We apply Bitwise AND to our settings value and that constant. What happens? Let's look at it. In the settings variable, other bits might be set too. But the way when I say a bit is set, I mean the bit equals 1. When we apply this operation, Bitwise AND clears all the bits except the first one. The first one will stay set because by the rules 1 and 1 gives 1. Then we compare the result to that same value. If they match, that means the bit is set and therefore the fan is on. If the fan were off, that is, the bit was 0, then the result of the operation would also be 0 because 0 and 1 gives 0. That means the if condition would be false and the else branch would run. Let's run the program twice. The first time the fan will be on and the second time it will be off. Let's move on to the next bit, the second one. Same idea here. You can create a constant that gives it a readable name. Notice that this time it's not the first bit that's set, but the second one, because that's the one responsible for the rotation status. Then we analyze that bit with similar code. You can try checking for yourself what happens when the second bit is binary. In binary is 0 or 1. In our first set of settings, it's off, so we should see the message in the else block. Let's run it and see. One important thing here. Notice the extra parentheses in the condition. They're required because bitwise operators have lower precedence than comparison operators and some others. If you remove them, the comparison will happen first, and its Boolean result, meaning 1 or 0, will then be used in a bitwise AND with that value. That produces some number, which then gets converted back to bool for the if. So get into the habit. When you work with bitwise operators, add extra parentheses just to be safe. Now things get a little more complicated because we've got 4 possible values, or 2 or 3. No speed, low, and high. That's 3 combinations. You can, of course, create 4 constants or 3 constants for them just to have readable names for those combinations. Then you do similar checks. Let's run it and look at different combinations. You might say, constants take up memory. You made so many of them that this isn't really optimization here anymore. We won't fit into 1 byte. First of all, the compiler usually inlines constant values, so they don't actually live in memory. Second, you could hardcore those values directly into the conditions instead of using constants. Hardcode means you literally write the number instead of a readable name, and you can always add comments nearby to explain what the values mean. The main thing is understanding how the operator works and what it's for. And that's not the only use of Bitwise AND either. With it, you can also clear certain bits in a value. Let's move on to the next example. We'll use the same byte alias and the same fan settings. We see that the fan is on. How can we turn it off? We could just assign 0 to the variable, but then all the other bits would be cleared too. Those might matter in other cases, so our goal is to clear only one bit, the rightmost one. We can first check whether that bit is set to all, using the check we already know. Then we can clear it like this. We take our value and apply Bitwise AND to it together with this number. How does that work? In that number, all bits are set except the rightmost one. When you use the operator, we get a result where all the bits stay the same except the last one. It gets cleared. So the 0 bits stay 0. Those two ones stay ones, but the rightmost bit disappears because 0 and 1 with this operation gives 0. As a result, we get a number where all the bits are the same as before except the last one. It's turned off, and we assign that value back to our variable. So let's summarize. In programming, Bitwise AND is most commonly used in two cases. First, to check whether a specific bit is set in a value. Second, to clear bits in a value. Let's go back to the first example. There is some commented out code there. Imagine we decide to add a third speed level when both bits are set. Would the third if work in that case? That is, we add a constant called fan level speed 3 with this value. The thing is, that code wouldn't work. Why? Because if we run the program and set both of those bits before the check, the first if will still trigger instead of the third one. That's because here we're first checking whether the third bit from the right is set. And it will be set in two cases, when the speed is low and when the speed is very high, meaning when both bits are set. So to fix that, you need to check for the third bit first, for the third speed first, where both bits are set, and only then check them individually. If both bits aren't set, then you check whether the left one or the right one is set. If the right one is set, the speed is low. If the left one is set, the speed is high or medium. Now imagine we want to check whether there is any speed at all. If both bits are 0, then there is none. And here we run into another problem. I created a constant that equals 0, meaning the relevant bits are cleared. Let me remind you that with this kind of code, we're checking whether a bit is set. But here the condition will always be true, even if the bits are set. Because if you apply Bitwise AND to any value together with 0, you always get 0. You can solve this by removing that fourth condition and just leaving a normal else instead. But we still have other operations left. For example, how do you check the opposite, whether the bit is cleared? Or how do you set a specific bit? For that, you need other operators. Let's move on to the next operator, Bitwise OR. First, I'll explain how it works. It's similar to the logical OR operator, except that while the logical one compares conditions, this one compares numbers bit by bit. The rules are simple. If at least one of the operand bits are 1, then the final bit is also 1. Only when both bits are 0 does the result become 0. Let's look at the example in the comment and read it from left to right. 0 and 1 gives 1. 0 and 0 gives 0. 1 and 1 gives 1. 1 and 0 gives 1. 0 and 1 gives 1. 0 and 0 gives 0. 1 and 1 gives 1. And 1 and 0 gives 1. That gives us the number 187. Now we can move on to some practical examples. Bitwise OR is used to turn on a specific bit or a group of bits inside a number. For convenience, I moved the code that prints all the fan information into a separate function. I didn't change the code here, so I'm not going to explain it again. So let's try to turn on all 4 rightmost bits. To do that, we can reuse the constants that previously represented which bits should be on. Before, we used them to check whether a bit was set. Now we can use them to actually turn bits on. We do it like this. We apply the Bitwise OR operator to our variable together with those values. That way we enable the bits one by one. You can write out a similar comment with the calculation yourself to see how the bits change as a result of this operation. But we can simplify those 3 lines by replacing them with a single one where we chain these operators together. If we run the program, we'll see that the first, second, and fourth bits are now turned on. So with Bitwise OR, you can enable individual bits. I want to say something important here. I'm showing you the ways I personally use these operators and that I've run into many times. But that's not their only use. You might come across other examples too. The key thing is to understand how they work. Let's move on to the next example. There's the Bitwise operator called exclusive OR or just XOR. It's also a binary operator, which means it needs values on the left and on the right. It works on each bit separately and produces a final value in that position. But how? Pretty simply. If the bits are different, the final bit is 1. If they're the same, it's 0. In our example, we've got 2 zeros that match here, then 2 ones that match, and further to the right, the same situation repeats. The other bit pairs are different, so wherever they're different, we write 1. Wherever they're the same, we write 0. And again, the question comes up, why do we need this operator? Well, thanks to it, you can toggle a bit from one state to the other without checking it first. Imagine you've got a variable that controls the fan settings and you don't know whether it's on or off, but you need to flip the rightmost bit. So if it's on, turn it off. If it's off, turn it on. Here, we have a variable with a specific value. The first printout shows that the fan is off. We want to turn it on. To do that, it's enough to write this operation. We apply this operator to our settings and the rightmost bit. The result is a number where all the bits stay the same except the rightmost one. It gets flipped. The second printout shows that the fan is on. If we apply the same code again, we'll see that the fan is off. So you can use this operator to toggle bits without needing to know whether they're currently set or not. Let's move on to the next operator. This is the Bitwise NOT operator or Bitwise Inversion. It's a unary operator, which means it only needs one operand on the right side. It takes every bit of that number and flips it to the opposite value. Here we've got some number. We apply Bitwise Inversion to it and get a new number. What does it look like? It looks like this: 11001100. In other words, all the zeros became ones and all the ones became zeros. In the previous lesson, I talked about how numbers become negative. We took all the bits of a number, inverted them, and then added 1. That's how we got a negative number. Now we can prove that in code. We take the number 10, apply Bitwise Inversion to it, and then add 1. We should get -10. Then we add 10 and -10, and the result should be 0. Let's run it and see. We can use this operator together with Bitwise AND when we want to clear a bit. Let's go back to example number 2. There, I used a number like this to turn off the first bit. But now, we can just use Bitwise Inversion instead of creating extra magic numbers. We take our constant, apply inversion to it, and the code works the same way, only now it looks clearer. Let's move on to the next operators. We've already run into these before, and you probably see them in almost every lesson. These are the Bitwise Shift Left and Shift Right operators. Their job is to take a number and move all of its bits to the left or to the right by a specified number of positions. Let's take the familiar number in binary form. Bitwise shift operators are binary operators. On the left, you write the value whose bits you want to shift. On the right, you write how many positions to shift by. Both operands have to be integer types. Both operators return a new number with the bits already shifted. First, I try shifting all the bits one position to the left. Watch how the number changes. The two rightmost ones move one position to the left. The next two zeros do the same, then two ones, and then two more zeros. But our variable only has 8 bits, so a 0 gets inserted on the empty spot on the right. That would make 9 bits, so the leftmost bit just falls off. And we end up with this combination. Notice that these operators, like all the previous ones, don't modify the variable itself. They give you a new value. And you can see in the next piece of code how I keep shifting the bits by different amounts to show that zeros will always be added on the right, and over time all the set bits in our number will disappear. That was the example with the left shift. A right shift works the same way, just in the opposite direction. All the new bits on the left will be zeros, and any extra bits on the right will simply drop off. There's one important detail to mention. If you shift a number in either direction by an amount that is equal or greater than the total number of bits in the type, you get undefined behavior. So that's something you should avoid. Our byte type has 8 bits, and if we try to shift by 8 or more positions to the left or right, the behavior is undefined. With negative numbers, things get more complicated. Take the number -10. For the short type, it looks like this in binary. If we shift a negative number to the right, ones will be added on the left instead of zeros. If we shift a negative number to the left, we always get undefined behavior. But in practice, shifting bits on negative numbers is almost never used. These operators can be combined with others to work with bits in a few useful ways. For example, you can turn bits on, turn them off, or toggle them using commands like this instead of manually writing large binary numbers. In these examples, I'm working specifically with the third bit if we start counting from 0. Or you can extract individual bits from a number and store them in separate variables like this. If you don't understand how that works yet, you can just convert all the values to binary and do the operations by hand on paper. That's not the only way to use these operators, but once again, my goal here is to explain how they work in general. But you've already seen these operators when working with cout and cin. So are bits being shifted there too? Nah. What's happening there is something called operator overloading. That's when you create a function whose name looks like an operator. In other words, what's actually being called are functions with full names like this. You can see their signatures if you hover over them in your editor. In the future, I'll teach you how to overload operators yourself. Why was that done here? Because the bitwise shift operators look like arrows that point in a direction. The C++ library designers decided that instead of calling functions like stdcout_print or stdcout_enter, it would be clearer to use overloaded versions of the bitwise shift operators. That way, when you work with cout, you can tell that your information is being sent into the cout object, basically to the screen. Take this text and send it to the display. And with cin, which you can think of as the keyboard, you see the command take input from the keyboard and put it into the variable. These operators just help show direction, but under the hood, they're regular functions. Let's move on to the final operators, compound bitwise assignment operators. These are operators that combine all the ones we talked about in this lesson with assignment itself. You've already worked with compound operators when doing math operations on numbers. I took all of today's examples and rewrote them using these operators. With them, the code looks simpler because the result of the operation is immediately written back into the variable without having to repeat the variable name. In the comments, I wrote that these operators expand into. You take the variable, perform the operation with it, and then store the result back in that same variable. And one last thing. Bitwise operators have low precedence. So if you want to print the result of some bitwise operation to the screen, make sure to increase that operation's priority by using parentheses, otherwise you'll get an error. And that's the end of this lesson. Thank you for watching. If you enjoyed the video, you can support me in the following ways. Give this video a like, leave a comment below, subscribe to the channel if you haven't already, or send a donation, either through the link in the description or by using the thanks feature on YouTube. Also, don't forget, any theory is meaningless if you don't reinforce it with practice. I have separate practical lessons available only to channel sponsors. In those, I give lots of exercises. I give lots of exercises based on all the lessons on the channel, and I also show how to solve them. So if you want to really grow as a programmer, consider becoming a channel sponsor to get access to the practical lessons. See you in the next lesson. Bye everyone.